Alright, welcome back. I'm going to do a little quick review series on some key concepts. The first one is on polynomial functions. So polynomial is an expression made up of a bunch of terms where the variables that are used have only positive integer degrees. And what I mean by that is that, let's say for example, like degrees are the exponents of a function, like exponents of a variable. So x cubed, that is a monomial function, but like it kind of falls into polynomial. We still call monomials polynomial, even though it's not really. It's categorized in this family. But the degree, the exponent, must be a positive whole integer. If you have an x cubed plus x to the 1/2, that is no longer polynomial. Like minus 1 over x. If you do 1 over x, that's actually x to the -1. It's not a polynomial. So this, I think we are good at recognizing when things are polynomial or not. So let's actually just skip ahead and let's start graphing. This is way more complex than what you'll be tested on, but you have had experience with something like this. So I'm fine showing it to you because I think it shows a lot of tricks. And anything that is not covered, like this is not a full comprehensive like overview of unit 1, but I think is a good example to show a lot of concepts. And like, if you are missing anything, it's good to like be like, oh, like I need to go back to my notes, go back to my homework, go back to like any past assignments to like see like what am I missing. I'll show you the textbook as well. So I have my function f of x equals this big polynomial, 4x to the 4th minus 16x cubed plus 13x squared plus 15x minus 18. When you're given a polynomial like this and you're asked to graph it as like the end goal, there's a lot of steps that we need to do. I'll show us the steps that I made in like a little notepad at the very end. But the first thing that we want to do is you want to find some key points. And key points for this function, for most functions, are x-intercepts. In other words, when is y equal to 0? What x values do I have? And this is something we've done a lot all throughout all of our math career. So we're setting like this whole thing equal to 0 and finding what value of x is this. And a quick thing that I got reaction is like, oh, I'm gonna factor it. But factoring at this point is very cumbersome. So if you remember, what we learned is like something called the rational root theorem or rational zero theorem. This I'm actually gonna type out because let's say the rational roots theorem. And this rational roots theorem is something that we utilize in this class. And what the rational roots theorem, I'll put it here. Let's get it a little bold. Does it change it? No, it doesn't change it. Something about this rational roots theorem is an easy way to find roots. And what this tells us is if I take all the factors of my last term, my constant term, and you take all factors of the coefficient of my leading term, my leading coefficient. So the factors for 18 is 1, we make it plus or minus. It's plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. And for 4, we have plus or minus 1, plus or minus 2, plus or minus 4. You might remember making this, like listing all these out. Rational root theorem, quick little summary of like our application is that getting any of these divided by any of those, our roots will be in there. Any clean, real roots will be like here. So for example, like 1 divided by 2, either positive or negative 1/2, that could be a possible root. And we use this because like it's more just guess and check and be like, we do it until we get a root and we can simplify this. Because once we find the root, we can now plug it in or like factor it out, knowing that this is a root, this is a factor, and get it simpler. Because like anything to the 4th power, I don't like factoring. So I could put it on the cube. And a cube, you might be able to factor, you might not. But if you can't, then be like, I'm going to do it one more time and get to squared. And once you get to square, once you have just this, we're fine either factoring it out or using a quadratic equation to find the other roots. And a little tip that I gave you guys is you will never have to use the rational root theorem beyond anything like 3. So don't immediately jump to, I'm going to try 18 divided by 2 or 18 divided by 1. That is not worth it. Like, don't use like, oh, I'm going to do like 1/4. So say try to keep it between 1/2, like 1/2 up to like 3. Like that's like our range kind of for using this. And we always start with like 1. So I'm going to start with positive 1. 2 ways to test it. One is like if you are not as confident with it, and then you could kind of double check, but you could jump straight into synthetic division. Or if you want to see like, is this a root? If it's a root, plugging it into my function must make it equal 0. So I'm going to show that first, and then we're going to now divide. So I'm going to try one that I know that might work. Like I'm going to try out 1. Be like x equals 1. I'll try this one out. So when x equals 1, I have 4. I'm just going to speed through this. 4, 1 to the 4th is just 1. Actually, I'll take it slow for the first one. 1 to the 4th minus 16, 1 cubed, plus 13, 1 squared, plus 15 times 1, minus 18. 4 minus 16 plus 13 plus 15 minus 18. And at this point, does it not work? Let's see. 4 minus 16, negative 12, plus 28, minus 18. And yet it doesn't work. Yeah, it doesn't work. Because I have like negative 30 plus 28 to get negative 2. So note that negative 1, like positive 1, does not a root. So I could immediately just get rid of 1. If you're good at synthetic division, we could like make it what to divide by. And honestly, synthetic division is pretty easy if you can do it like accurately. If you keep track. So 4 just goes straight down. 4 times 1 is 4. Negative 12. Negative 12. 1. 1. 16. 16. Negative 2. It doesn't work. So actually, let's now skip ahead. I actually prefer synthetic division. So I'm going to try negative 1. Negative 1 for 4. Negative 16. 13. 15. Negative 18. Bring the 4 down to get 4. Negative 4 to get negative 20. 20 to get 33. 33. Negative 33 to get negative 18. Negative 18 times negative 1 is positive 18 to get 0. And once you get 0, you know that it factors out nicely. So rewriting this, I have x plus 1, because that gives me this as the root. Make sure you flip it. X plus 1 times 4x cubed minus 20x squared plus 33x minus 18. It looks kind of worse because I have 33 and a negative 20. Those are bigger. But it is the correct first step. And now I see, can I factor this more? Maybe I'm able to force factoring it. But I'm like, I don't want to do that. I'm going to go straight back into, and these roots still work. So let's continue just practicing it. I know positive 1 does not work because I tried before. But I'll try negative 1 again. Does negative 1 work? Negative 1 for 4, negative 20, 33, negative 18. Synthetic division becomes 4, negative 4, negative 24, positive 24, 57, negative 57, and clearly this does not work. So I'm going to stop right there. So negative 1 does not work anymore. Looking back up, what are some nice ones? I'll move on to 2. 2 over 1, I have positive 2. So 2. 4, negative 20, 33, negative 18. Bring the 4 down. 8, negative 12, negative 24, 9, 18, 0. So it works. And now I rewrite everything. I personally like to rewrite everything so I don't forget. I am quick to forget. So I'm going to bring the x plus 1 down. Now the x minus 2. And then 4x squared minus 12x plus 9. At this point, it should be good enough that we could use a quadratic equation or factor this out. I could skip factoring, but like I'll just use a quadratic equation. It does factor out nicely. But let's just use a quadratic equation because we haven't done much with that in this class. X equals negative b plus or minus the square root. You will not need to use this, if at all, on the exam. So 12 plus or minus 144 minus 4 times 4 times 9 all over 8. 12 plus or minus 144, 16 times 9. 16 times 9. It's 144. Over 8. 12 over 8 gives me 3 over 2. 3 halves. And this is telling me both my zeros are 3 halves, which is a key thing to memorize. Both my zeros, I have 3 halves and I also have 3 halves. So both my zeros are 3 halves. So bring this all down. I have x plus 1, x minus 2, 4x squared minus 12x plus 9. So my zeros are negative 1, positive 2, 3 halves, and 3 halves. 3 halves twice. Those are my x-intercepts. That is step 1. It's a big step, a lot to do. This one we divided twice, but we haven't had to divide twice since like that one long homework that I gave out, just to practice and stay organized with our work. Now we count the multiplicities. Multiplicity means like how often does that 0 come up. This only shows up once, only once, but 3 over 2 shows up twice. It has a multiplicity of 2. If you have an even multiplicity, that means that it bounces. For these, it just passes through. And that with multiplicity 2, it bounces. And when we have bounce is like the graph of x squared. X squared just bounces. It touches the graph at 0, 0, and just bounces up. Whereas the graph of like x, f of x equals x, it just passes straight through. So that is what we mean by it bouncing. So that's step 1. Get all your roots. Step 2, identify multiplicities. Step 3, find your y-intercept. This honestly could be done first, but y-intercept is when you're touching the y-axis. Therefore, your x must equal 0. So let's look up at our original equation and see when I plug in 0 into this graph, into the function, what do I get? And you should get negative 18. This is something that I think you could try and like see what can I do, see if there's something quick. But like make sure you see like everything has an x except for the constant. So we have negative 18. You have y-intercept at y equals 18. The final thing that we need before we graph is our end behavior. End behavior only relies on the leading term. So once again, we look back at our original. I have 4x to the 4th. the leading term is the only one that matters because the leading term, like exponents, are very, very strong. Anything to the fourth power, like x to the fourth power, and then like we have x to the cubed, it doesn't matter like if this is like 4 and this is like 4 million. End behavior means that the x is going to infinity. So this x will be way bigger than the 4 and 4 million. That like once we pass 4 million, this is going to be so much bigger than that. So we always look at just the highest degree. Doesn't matter what the coefficients are. So I don't care about x cubed, I don't care about x squared, I don't care about x. I just care about this x to the fourth. So I look at this, and there's two things I care about. One is the sign of the coefficient, and also the degree of the variable of the term. These two things combine to tell me what my end behavior should be. So you can memorize the chart that we made in class, or you could also be like, as x, let's start with the kind of easy one to work with. As x is a big number, as x goes to positive infinity, what happens to my y? What happens to my function? So I plug in a big number, I put it to the fourth power. All I care about is my sign. If I have a big number, I have a positive number, put it to the fourth power, it's still positive. Because even exponents will always be like positive. And then I multiply it by positive 4. So I have a positive that got to the fourth power, so it's still positive, times a positive 4. So as x goes to positive infinity, y goes to positive infinity. On the other hand, as x goes to negative infinity, a negative number to the fourth power becomes positive. A positive number times 4 stays positive. So as x goes to negative infinity, y goes to positive infinity. And this is true because even coefficients, even degrees, not coefficient, even degrees, to the fourth power, to the second power, to the sixth power, to the 12th power, the end behavior should be the same. They should both point in the same direction, either both positive or both negative. This one we have both positive. Now with everything set, I'm going to bring it all down. So I'm at y-intercept at 0, at 18, y int, at negative 18. I misspoke. Y int at 0, negative 18, x int at negative 1, 0, 2, 0, 3 over 2, 0 with a multiplicity of 2. Now we graph this. Graphing it, you will be given grids. I'm just going to sketch it just like how we did in trig. So I'm going to plot everything. I have my negative 1, 0. I have my, let's actually label this, negative 1, 0. I have my 0, negative 18. I have my 3 halves, 3 over 2, 0. And then I have my 2, 0. And this, I think we definitely did it for rational functions. We might have done it a bit with polynomial functions. But the signs for this behavior can be seen just by seeing my multiplicities and my intercepts, and also my end behavior. So in the next video, we're going to make a little number line that goes through like finding each sign, but I don't think that we need it for this polynomial functions. So I must, as x goes to negative infinity, I must go to positive infinity. And I must touch every single point that I graphed. So I must go down here, touch negative 18, come back up, and I see I have a multiplicity of 2. So I must bounce and pass through. And this is my graph. I must touch all my x-intercepts. I must touch all my y-intercepts. I pass through negative 1 and positive 2 and bounce at 3 halves. And my end behavior is both going to positive infinity, and these are. To confirm this real quick, I have my Desmos graph. Let me make it into negative. here's my Desmos graph. And let me also, this is the factored form, but I'm just gonna write it like, actually, -16x cubed plus 13x squared plus 15x minus 18. And it is the same graph. I have 0, I have 0, 0. Let's label these. That should be good enough. And also all the way down here, I have this as well. So we see as let me actually change this to be like that, so we can see a bit more. We see I have a intersect here, intersect at these intersections, and I bounce at 1.50 or 3/2. And I go to positive infinity on both ends. So that is it for polynomial function, graphing polynomial functions. One more thing you can do if you want to be doubly sure about your graphs is like, oh, I want to actually check that I bounce at this point. You could pick a point in between, like 3/2 and 2. I could pick a 1.75 and plug it into my function, and I should get a negative value. You could plug in 5 into my function, and you should get a positive value. You should plug in like -20, and you should get a positive value. Those are nice ways to check to see, like, is my graph working correct? Like, do I need to bounce here or do I not need to? And you can either check it by looking at multiplicity, or you check it by looking at your signs, like plug in values and see what you get. Okay, so the next video will be on rational functions. Hopefully this was helpful. Oh, I forgot to, here's like the little steps that I use. Polynomial functions, nice and simple. You could sneak peek on rational and much longer. Find all zeros, identify multiplicities, your y-intercepts, and behavior. Once you have these three, the order of it doesn't matter that much. And you want to draw the function. You plot all your points, you label your points, you draw your function. Good luck.